Hello, I'm Chunhui. I'm from the University of Luxembourg. Today I will present a work about system testing of timing requirements based on use cases and timed automata. This work has been developed under the collaboration with our industry partner, IE, which is a leading company in the automotive industry. Timing requirements are pretty important when testing on safety critical systems, since a simple violation of timing requirements may put the human lives in danger. Here is an example of timing requirements from the automotive domain, which state that airbags should be fully deployed within 50 milliseconds when a crash event is detected. So we can imagine that any delay during the detection of a crash event or the deployment of an airbag may let the driver lose his life. So this is another example we get of timing requirements get from the automotive domain, which has been used as a case study in this work. So this requirement is about the detection of the overheating. So a car control system should signal overheating to the driver when the temperature exceeds a safety threshold for a given time. This requirement is important is because most of safety critical components are not reliable when a car is overheated. For example, the airbag control. A refinement of the timing requirements about the detection of overheating are the following. First, a temperature error can be qualified or signaled to the driver if the overheating is detected for at least 3100 milliseconds. These requirements prevent the error detection is too fast to avoid the signal tangling. On the other hand, a temperature error should be qualified no later than 4800 milliseconds after the overheating is detected. So this requirement specifies the maximum time of the detection of overheating. The objectives of this work are the following. First, we want to automatically generate the test cases to stress the timing requirements with a minimum modeling overhead. Secondly, we want to identify the input sequences that increase the chance that the system will break in their timing constraints. However, the context strongly influences the solution. Our solution is quite common in the industry practice. First, the functional requirements are captured through a analyzable form of use case specifications. So here shows an example of the use case used in our context. The use case is in an analyzable format is because it is written by using a set of restriction rules and by usage of set of keywords. So here the keywords is showing in capital letters and in the color blue. Secondly, the timing requirements are modeled either by UML state chart or timed automata. So in this work, we choose to use a timed automata. Lastly, the functional test cases are automatically generated from the use case specifications by using a UMTG methodology. UMTG is our previous work on functional requirement testing, which has been published on the ICST 2015. Basically, the UMTG methodology takes a set of use cases and a domain model and a set of OCL constraints as the input, and automatically generate test scenarios to cover the basic flow and each of the alternative flows for all the use cases. And finally, by using a test adaptation approach, which automatically translates the test scenarios into executable test cases. So if you are interested in the UMTG methodology, please refer to our ICST paper. Under such a context, the strategy for testing timing requirements are the following. First, we choose to use timed automata to model the timing constraints. since this is the current practice in our industry partner. Since the automata are high-level missing information about concrete test inputs that may lead to state transitions. So our solution is we rely on use case scenarios to identify the test input that triggers state transitions. Then we rely on edge coverage criteria to identify test sequence. Now, since the test sequence generated by edge coverage only makes sure the timing requirements has been covered, but not aiming at to stretch them. So then we integrate the meta-heuristic search approach to build a test suite that effectively stretches the timing requirements by maximizing the test case diversity. Our approach was named TAUC, or TALK, Test Generation Combining Timed Automata and Use Case Specifications. TALK works in 5 steps. So now I will explain these steps. The first step is analysis and design. All the modeling work should be done in this step. So the question is, what should we model? So first, it's quite obvious that the engineer should create the automata that captures the timing properties of the functionalities under test. For instance, the qualification of the temperature error. It's also very important that to create the automata that model the environment. For instance, the automata that captures frequency of arrival of interrupts, messages, and the input from sensors. These informations are allowed to generate complex test cases that combining interrupts and messages that are more likely to let the system break their timing requirements. The automata that capture timing properties of functionality and the test was named Timing Requirements Automata. So here let's take the functionality of error qualification as an example to show how the timing requirements automata looks like. So first we have an initial state, not detected, not qualified. And when an error was detected, it will move to the state detect but not qualified. If the error was immediately disappeared, so then it will move back to the state not detected, not qualified. So according to the requirements, if the error was continued detecting for 3100 milliseconds, so then they can move to the state detected, not qualified. So we put a timing guard x greater or equal than 3100 milliseconds to the transition. So the requirements also said that if the error continue detecting for at most 4800 milliseconds, it should be qualified. So which means that the error can't stay in the state detect not qualified for more than 4800 milliseconds. So we put invariant for the state with the timing constraint that x smaller or equal than 48 milliseconds. So the complete model also captures the process of error dequalification. So for each of the transitions, there's made some updates on the state variables. Here, the legend shows what's the meaning of different labels. The automata that model the environment is named environment automata. So for instance, a timer interrupt is generated every 15 milliseconds. And the DMA interrupts was generated at a frequency no faster than every 51 milliseconds. Restricted by the communication bus, the messages sent through the bus should be below the rate every 15 milliseconds per message. The second step is identify the functional scenarios. This step was automated by the UMTG when testing the functional requirements. So in order to minimize the modeling overhead, we want to we want to capture some useful information available in the use cases. So this was done by identifying the dependencies between the timing requirements automata and the functional scenarios. So this information are useful to translate the abstract test activities into the concrete test inputs. So what are these dependencies? Let me explain the dependencies by showing an example of simple test generation based on coverage. So a coverage-based test generation may suggest to test the path marks as in orange. So in order to test the timing requirements on error qualification and dequalification. So in order to test this path, we need a test case that first to generate a detected event and then wait for 4800 milliseconds and then trigger an anti-detection event and then wait for 81 milliseconds, 100 milliseconds. So there leaves a big question here is how to translate the error detected event into a concrete test input. So unfortunately, most of existing work not addressing such a problem. So our solution is by reusing some information available in the use case specifications. So let me explain how we do it. So for example, from the use case specification, we can find there is a conditional step that the system validates if the temperature is valid. If the condition is not hold, the alternative flow will be taken. We can see that in the alternative flow, error was set as detected. From the OCL constraint that attached to the validation step, we can see that a validated temperature should be between 0 and 55 degrees. So from our previous work, the UMTT will generate the test input, for example, temperature equal to 50 degrees. That leads to a detection of the error. Thus, we can say that the error detection can be generated in the use case scenario of temperature is not valid. In other words, the test input that allowed to execute the test scenario can trigger the test event for the error detection. So the first dependency between the timing requirements automata and the functional scenario is a scenario brings a system into a specific state. On the other hand, the execution of the functional scenario may also depend on the state of timing requirements automata. For example, in the fourth step of the basic flow, the system validates that there is no error is qualified. If the condition is not held, then the alternative flow will be taken. From the OCL constraint attached to the validation step, we can know that the precondition to execute the scenario that covers the alternative flow requires at least one error was in the state with the state variable is qualified equal to true. In other words, the dependency is a scenario can be executed only if the system has reached a specific state. Once we have identified the dependencies, in the fourth step, we generate a timeless test model that captures the dependencies and all the information from the analysis and the design phase. The timeless test model contains the augmented timing requirements automata and the generated scenario automata plus the environment automata. By specifying the coverage criterion into a reachability problems, we rely upon UPO to generate the execution scenarios to cover all the transitions that related to the timing requirements. Since the test case generated so far only guarantee the edge coverage, but not aiming at to stretch the timing requirements. For this reason, in our approach, we include a meta-heuristic search approach that iteratively modify the test case generated by UPO to build a test suite that effectively stress the software timeliness by maximizing the test suite diversity. The diverse test case allow us to execute more and diverse paths including the same relevant edges, and execute paths with a diversity of inputs, interrupts, and messages to increase the chance to trigger the timeless fault detection. We evaluate our approach on an industrial case study, BodySense. BodySense is an embedded system for detecting occupancy status in a car, which developed by our industry partner. The goal is to evaluate the effectiveness in terms of fault detection rate compared to the current practice at IE. In order to evaluate our approach, we first created a set of mutants, which represent the faulty version of the system. Mutants are created by applying different mutation operators on the original model. The mutation operators considered here are the ones may impact on the timing requirements. Then we simulate the test case execution on the model level and compares the fault detection rate to the test rate generated by random testing and the expertise-based manual testing. We generate a test weight with different size from 25 to 122. The size of 122 equals to the size of the manual test weight. From the table, we can see that talc is much more effective than both random and manual testing, even with a much smaller test weight. For example, the test weight with a size of 75 covers 91% of the faults. Please note that all the faults covered by random testing and the manual test are also covered by our approach, and there are a small percentage of faults not covered by our approach are also not covered by other two approaches. Limited observability is the reason why talc can't cover all the faults. Details are presented in the paper. To sum up this talk, we first show the importance of the testing of the timing requirements for the safety critical systems. Then we present talc, which generates system test cases to stress the timing requirements based on the use case and the timed automata. We evaluate the effectiveness by comparing the fault coverage rate with expertise-based manual testing and the random test. The evaluation result shows that talc was much more effective than the other two approaches, even with a smaller test weight size.